in the previous two lectures, we have talked about some concept of probability and random variable, then jointly distributed random variable. Now, in the third lecture of this particular course, we are going to talk about conditional distribution of random vectors, okay, or random variables. So, what is the conditional distribution for discrete random variable? We will first start with the discrete random variable and then we will proceed to the continuous random variable also, or continuous random vector also. So, in case of the discrete random vector, how we can talk about the conditional distribution, and the idea in this case is very simple. So, suppose that x y be a discrete random vector with joint probability mass function f x y, and suppose that the marginal PMF of y is f of y. So, what is the marginal PMF of y? That is nothing but the y, if x y is discrete random vector, it can be shown that y is a discrete random variable. So, it has a PMF. So, that PMF is called the marginal PMF in this context, and in this case we can talk about the conditional PMF of x given y equals to y is given by this particular expression. Okay. And what is this expression? If you see that from the definition of joint probability mass function, the numerator is nothing but x probability that x equals to y and y equals to y divided by probability that y is equals to y. The denominator is probability that y equals to y. That is directly from the definition of joint PMF and the marginal PMF. Now, so this particular quantity is nothing but this conditional probability. So, that actually nothing but probability that x equals to x given y is equals to y. Okay. So, that is basically the conditional PMF, and this conditional PMF is defined only if this probability is strictly greater than 0, which basically mean that this the f of y at the point small y has to be strictly greater than 0. Okay. So, this condition has to be there, otherwise I cannot define the conditional PMF at the point for given y equals to y, okay, for given capital Y equals to small y, that is needed. Now, from the definition it is clear that this function is basically a probability mass function. Of course, the conditional probability mass function, but it is a probability mass function. So, I can write the corresponding that conditional CDF, and which is basically coming from the fact that CDF is nothing but probability x is less than equals to x, but I know that the value of y is small y, the value of capital Y is small y. So, in this case this probability I can just sum it up the probability up to the point small x. So, that is what basically written here, and again this probability is only meaningful if the probability of the given event is strictly greater than 0. So, that basically mean that f of y at the point small y is strictly greater than 0. Okay. So, in this way I can talk about the conditional distribution for a discrete random variable, and it is a very important thing, as you see in this course. In most of the cases we will going to talk about the conditional distribution. Okay. So, it is the important thing. Keep in mind that in case of the discrete random variable, the conditional PMF of x given y equals to y is defined by this particular expression, and this is basically nothing but the probability x equals to x, y equals to y divided by probability of y equals to y, and this is only defined if the probability y equals to y is strictly greater than 0. Okay. And this is a function, note that this is a function from R to R, this is a function from R to R, or rather I can write it a function from R to 0 1, because it is finally a probability. So, R to 0 1, keep this function is a function from R to 0 1. And now, of course, we can talk about the conditional CDF, and that is nothing but if you take the sum of the conditional PMF over the appropriate set, appropriate points, we get the conditional CDF. Okay. So, So again, the idea behind this conditional distribution or conditional PDF just same as that of the conditional probability, because it is finally a conditional probability. And the idea is that, well, if I know that y equals to y has occurred, what is the probability of x equals to x has occurred, okay? Or if I talk about the conditional CDF, that is that if I know that y equals to y has occurred, I try to find out what is the probability that x is less than equals to small x. Let us proceed, okay? Now we can talk about something again very important concept is conditional expectation for discrete random variable, and idea is very simple. As I have mentioned that f of x given y, this one is basically a conditional PMF. So, finally, it is basically a PMF, okay? It is a conditional PMF, fine, but it is basically a PMF. So, with respect to this PMF, I can try to find out what is the expectation of the corresponding random variable. So, that is basically exactly that, and in this case little bit generalization I have written that, well, instead of taking only that random variable, maybe I can talk about some function of the random variable. Okay. So, if I try to find out expectation of h of x given y equals to y, so I try to find out that if I know that y is equals to y has occurred, what is the expectation or what is the long run average of h of x. Okay. Given y equals to y has already been occurred, I try to find out what is the average of h of x, that is basically this one, and that one basically I can find like this way, that the simple thing, and basically that here because I am trying to find out the conditional expectation, here the PMF is basically the conditional PMF, that is the conditional PMF. Okay. Conditional PMF of x given y equals to y. Okay. So, that is basically that thing, and in this case also this absolute summability is needed, and that basically mean that again same as before, that it is nothing but summation x such that x y belongs to the support x y that you know that mod of h of x multiplied by the conditional PMF x given y is less than infinity. Okay. That absolute summability basically mean this in this case. Okay. So, let us now proceed to the continuous random vector. So, in case of the continuous random vector, the joint PDF, the probability density function of x given y for given y equals to y is defined by this expression. So, just note that the expression is just same as that of the discrete random vector, that joint probability density function divided by marginal probability density function, and for discrete random vector it is joint probability mass function divided by marginal probability mass function. So, the definition is exactly same, but this condition again is needed because I am dividing by that probability density function at the point y. So, that condition has to be true. If it is 0, then I cannot, of course, I cannot define this ratio. So, that is why basically this has to be true. Okay. Now, again I can talk about the expectation. The definition of the expectation is same as before, just the summation need to be changed with the integration, and again this condition is needed, otherwise that joint density function is not defined. Okay. And then this is the expectation, and we say the expectation is finite or expectation exists if the absolute integrability is there. If not there, we say the expectation do not exist or expectation is not finite. Okay. So, let us proceed. Okay. Now, let us talk about something which is very useful in computing the expectation. Okay. So, we can compute the expectation by conditioning. It is something like resemble with theorem of total probability. I can find out the probability of a set by conditioning on several other sets. The same kind of concept goes through here. So, what happens? Suppose I try to find out expectation of x, that I can, if y is another discrete random variable, I can find out expectation of x by this expression. So, what I did? I basically write the conditional expectation multiplied by the marginal probability, and I then take the sum. The idea is very simple. Suppose in a class there are two column of benches. Okay, in a class there are two column of benches, and the teacher is here. He is teaching to the class. Okay. Now, suppose the teacher want to find out what is the average height of the student in the class. The thing is that x is a random variable which denotes the height. Now, the thing is that the teacher try to find out what is the expected height. Okay, what is the expected height? That's basically teacher try to find out. Now, there are two ways to do this one. One is that, well, I measured the height of all the student in the class, and then I take the arithmetic average. That is standard way to do this one. Another way I can do this one is as follows. Suppose there are n1 students in this column and n2 student in this column. So, what I can do is that I first try to find out what is the average of this column. Maybe I call it x1 bar, and I call the average of heights of this column as x2 bar. So, then to find out the final average, I can do this one. It is n1 x1 bar plus n2 x2 bar divided by n1 plus n2. All of you know this formula. This is a very preliminary formula that we learn in school levels. So, all of us know this formula. Now, note that this one I can write as n1 divided by n1 plus n2 multiplied by x1 bar plus n2 divided by n1 plus n2 multiplied by x2 bar. Okay. Now, you see what basically I am doing. You can think this one as a probability that a student is in this column. Okay. And this one is again the probability. This one is again the probability that the student in the second column. Okay. Probability of first column, and this is the probability of second column. Okay. So, now what is this x1 bar? That is the average of this column, this is the average of this column. So, finally, what I have? Probability multiplied by the average given that the student in the first column. So, that is the conditional expectation. Similarly, plus probability multiplied by the conditional expectation of the height such that the students are in the second column. And you see that exactly same thing has written here. Just the thing is that if you take y is a random variable taking two values, one if the student in the first column, two if the student in the second column, and then this quantity, this thing, this summation, this expression is exactly the thing that I have written here. So, this one is, you can see as a generalization of the concept that you have done in your school level. Okay, that you have done in your school level, but of course, that has written in a general form in terms of probability, in terms of the conditional expectations. Okay. So, this is a very, very useful expression, useful formulas. We can see many a times that finding out of the expectation of x is quite difficult, but when you try to find out the expectations by conditioning, that become quite simple. Okay, expectation by conditioning, that become quite simple, and in our Markov chain part and then the subsequent part of Poisson process, we will actually see this kind of examples. Okay. So, this is for y discrete. Similarly, I can do it for y continuous. The only thing is that, okay, keep in mind one thing, this probability is basically same as I can write as probability mass function, marginal probability mass function of y. Okay. And then for continuous random variable, again the same standard thing is there, that well, integration has been, the summation has been replaced by the integration, and then probability mass function is replaced by the probability density function. Okay. So, these two are quite important, quite useful formulas to compute expectation by conditioning, and with that let us proceed, and the next slide we are going to see how I can compute probability by conditioning. So, this one again is a generalization of that of theorem of total probability. So, if y is discrete, this is given by this. If you compare with the last expression, in case of the expectation, this was the summation conditional expectation multiplied by marginal probability mass function. Now, when I try to find out the probability, it is nothing but the conditional probability multiplied by probability mass function for discrete random variable, and for continuous random variable conditional probability multiplied by probability density function, and then take the integration. Okay. So, that is what the thing, and this one actually directly comes from the expectation formula, because just keep in mind, if I have a random vector, this one which is basically a function which takes values 1 if x belongs to A and 0 otherwise, then it is very easy to see that the expectation of I A, the random variable I A, is same as the random variable I A takes two values, one is 1, another is 0. So, it is nothing but 1 multiplied by the probability of 1. So, probability that I A equals to 1 plus 0 multiplied by probability that I A equals to 0, because I A is a discrete random variable, it can only two values. Now, the second part does not contribute anything, because I have a multiplication by 0. So, that basically turns out to be probability that I A equals to 1, and I A equals to 1 if and only if x belongs to A. So, that basically turns out to be probability that x belongs to A. So, the probability that x belongs to A can be written as expectation of I A, or maybe if I write it correctly, maybe I just put the x here just for understanding, that maybe I can write x here. Okay. So, then everything goes like that. Now, you see that so that the probability can be written as an expectation, and this random variable generally we call indicator random variable. Okay. So, this random variable we call indicator random variable. So, probability of x belongs to a set, can be written as the expectation of that indicator random variable of the set A. Okay. And now, using this one, finding out this one is very simple, because see probability of E, the probability of E is basically I can write as probability expectation of I E of x . Okay. I can write as I E of x, and then basically this one continues. Then basically we can use the previous slides material, and previous slides material, that the expectation can be written in this form, and we can proceed, and finally we have that this expression hold true. And as I mentioned earlier, that that computing expectation by conditioning or computing probability by conditioning are very useful tools to find out the expectation or probability, and we will see some example as we go through with our stochastic process, with our Markov chain, with Poisson process in this particular course. With that, I stop and thank you for listening.